Thank you very much. Okay, so the lecture this year is, as you've heard, Just Add Water. Now, water is, of course, a substance that's familiar to all of us, but in the lecture today I want to show you perhaps some of the more unusual properties of this substance we know so well. Okay, now, many things contain water, and I'm going to start off with these crystals here of copper sulfate. Now, these are a beautiful blue colour, and this is because of the interaction of the water that they contain with the copper ions. And just by heating the crystals, we can actually drive out the water. So I'm using the Bunsen here to heat up the crystals, and we can drive out the water that's locked up in them, and we should see a colour change. So say the crystals are blue because of the interaction of the water with the copper ions, but once the water is removed, and we can see some of the water condensing in the neck of the retort here, well, the crystals are actually changing to a white colour. So you should be able to see some water dropping out. It's just about to drip out the bottom. There we are. I think we're just about to get a drop. There are some drops of water. So as I say, it's the water contained in these crystals interacting with the copper ions that gives rise to the blue colour. Now, many things contain water. Of course, we contain water, and our food contains water too. Now, this banana, for instance, well, we took this banana a while back, weighed 70 grams, and then we removed all the water from this, and then weighed it again, and it only weighs 20 grams. So that means about 70% of this banana is actually water. And once the water's removed, well, it's pretty solid. And in fact, we actually dehydrated this banana 4 years ago, okay? And so it's actually lasted pretty well. And as you know, if you just left a normal banana out, it would decompose pretty rapidly and go mushy and horrible. But that's because of all the chemical reactions taking place within that banana. But once the water's removed, well, these reactions don't take place any longer, and the banana keeps more or less intact. So they are a 4-year-old banana. Okay. Well, as I said, there's lots of water all around us. The Earth is about 70% water, the surface of the Earth. In fact, water is the most common substance on the surface of the Earth. Okay. We've seen that our food contains water, we contain water. Well, I have a little clip here now to show you what happens when the water's taken out of us. Now, this is a clip from the first Batman film, okay, where the evil penguin is going to dehydrate some pirates.
You'll feel nothing.
So he's got his total dehydrator.
I am merely going to temporarily extract every bit of moisture from your body.
And these are the guinea pigs.
Painless operation.
There's the water. Dehydrated. Now, I don't know if you've spotted it, but there are a couple of errors in that. Well, the first of them, as I'm sure you noticed, is, of course, that actually we've got much more water in our bodies than was taken out there. So, for instance, in me, I would have enough water in me to fill all of this up, all of this one, and all of that container. Okay, so there's an awful lot of water inside us. Well, that's the first point. The second point is what's left. There's just this little pile of dust. Well, actually, there's a bit more in us than just that. If you carefully removed all the water from a human, what you'd get left is this. Yeah, quite. This is a mummy that's been preserved. It's thousands of years old, and it's been preserved because all the water has been taken out of this. In the very dry conditions where the body was kept, the water was taken out, and much like the banana, this slowed down the chemical reactions that would normally take place to allow the tissue to decompose, and this is how it's lasted thousands of years. Okay. Now, water then, essential for reactions to take place. Most reactions take place in solution, and most reactions in biological things, of course, take place in water. It's very unusual to see reactions take place without a solution, without water there. Now, I do have an example to show you of a reaction between two solids which takes place without any water. So I have two solids here. These are potassium iodide and lead nitrate. Just mix them, that's better. And when I mix these, we should see a reaction taking place. I'm going to pour the two solids together. Okay. And maybe I'll get a white background for this. And you may be able to see where they're mixing, there's actually a yellow line in between the two of them. Okay. Now, if I shake this up, we get a distinct colour change. We see a yellow colour here now, and this is a reaction that's taken place between two solids. The lead nitrate and potassium iodide have formed, well, this yellow colour is due to lead iodide. It's very unusual to see a reaction between two solids. I also have the same compounds here, now dissolved in water. Okay? And mixing these two, the potassium iodide and lead nitrate, instantly form a bright yellow precipitate of the lead iodide that you saw. But the reaction takes place much more quickly in solution when the substances are dissolved, since they can intimately interact with each other. Now, I have another reaction now that I'm going to show you, and this one involves magnesium. Now, you may have seen magnesium before. Magnesium is a metal, so this is some magnesium ribbon, and, well, it burns with a very bright white flame, as you may already know. So I'm going to use the Bunsen burner here to light the magnesium, and you can see the intense white flame from this and some white smoke coming out here due to the interaction of the magnesium as it's burning with the oxygen in the air, forming magnesium oxide. Well, we can show this with a slide for the reaction. So we have magnesium reacting with the oxygen from the air, forming the smoke that we see here, magnesium oxide. Okay, well, that didn't involve any water whatsoever. Okay, so now I'm going to use the magnesium again, but this time start a reaction using a drop of water. So Mark has just brought on here a mixture of magnesium powder and silver nitrate. And the silver nitrate contains a lot of oxygen, and this is going to react with the magnesium, the oxygen contained in the silver nitrate. And I'm going to start this reaction, though it seems to be sitting there perfectly happy at the moment, but I'm going to start this with a drop of water. So I need some water. Just come around here to the water dispenser, get some water. So it really is just normal tap water. Actually, I'm sure it isn't tap water. It's very nice mineral water, of course. Yes. Okay, and now I have my long pipette, my special long pipette. And remember, the solids are just sitting there very nicely at the moment, no reaction. But as soon as I add a drop of water, so watch what happens when I add a drop of water. Okay, the reaction takes place. And you may well wonder what happened to the little aluminium dish that this was in. It's completely gone now. Okay, so a very, very violent reaction, but started just by a drop of water. And the water allowed the two substances to really mix intimately in order for the reaction to take place. I have one more demonstration to show you, started by a drop of water. This is with some Rice Krispies. Now, if any of you have seen some of my other lectures, you may have seen when I'm reacting Rice Krispies with oxygen in the form of liquid oxygen. And then we light it with a stick, and the Rice Krispies go up quite drastically. Well, this lecture, of course, is all about water. So I'm going to start this reaction with a drop of water. So the Rice Krispies are flammable. Okay? We can burn them. After all, this is what gives us our energy. But this time, rather than using oxygen, either from liquid oxygen, pure oxygen there, or the oxygen from the air, I'm going to use a solid compound called sodium peroxide. So I'm just going to sprinkle this over the Rice Krispies in much the same way you'd sprinkle your sugar on your Rice Krispies. Okay, just mix it up nicely. And again, no problem here. So the Rice Krispies, perfectly happy there. Nothing's happening until I add some water. So, drop in pipette, add a little bit of water in the same way you would add your milk in the morning. Maybe you'd add a bit more, but anyway. So we'll come round. So Rice Krispies, peroxide, and there we are. A rather violent reaction. Now, Rice Krispies, of course, give us our energy. It's one of the sort of foods that we can use to provide our energy. And you'll notice in the bottom, the burnt Rice Krispies, well, the container is actually red hot now, but in the bottom there's a sort of a black mass. This mass is carbon. This is one of the elements that's present in the Rice Krispies. In fact, many foods contain carbon in the form of a carbohydrate. And this sugar is, of course, an example of a carbohydrate. And this is the structure of sugar on the back here, sucrose. The black balls represent carbon atoms, the red balls represent oxygen atoms, and the white ones represent hydrogen atoms. And in the molecule of sugar, or sucrose, there are a total of 12 black carbon atoms and enough hydrogen and oxygen atoms to make up 11 molecules of water. So we can say that the sugar contains carbon and it contains, well, the elements of water. We say it's a carbohydrate. So sugar is a carbohydrate. Okay, and as I say, it's got enough elements there to make 12 atoms of carbon in every molecule and 11 molecules of water. Now, we can actually remove the elements of water from the sugar in a reaction using something that has a very strong affinity for water, and that's concentrated sulfuric acid. So I have some acid here, and I'm going to add the acid to the sugar. And this is a bit of a slow reaction. This is one that we need to keep an eye on, okay, during the course of the lecture. So we can already see that the sugar has gone a sort of a yellowy colour. This is much the same way if you're heating up some sugar, it caramelizes, it goes sort of brown first of all. Well, this is what's going on here. And eventually this will go black and form this. Okay, so this is one that we did earlier, right? And the black mass that we see here is actually the carbon that's contained in the sugar. Okay, so we've extracted all of the water. Okay, so far then we've seen examples where we can take water out of things. What would I add in the water back? So, for instance, our copper sulfate here, this white powder that we now have, if I add some water back to this, there's some water, add it back, it goes blue again. And this is, we'd say that the copper sulfate has been rehydrated and it's reformed the blue colour that we see due to the interaction of the copper ions with the water. Well, many things can be rehydrated. Of course, we use this stuff all the time. This is instant coffee. This is dehydrated coffee. We put it into our cup, add some water, rehydrate it, and we get our coffee back. Now, can everything be rehydrated? Okay, well, let's see what happens in the Batman film. We just have the lights down again. So now the penguin has smuggled the dehydrated pirates back into the Batcave, and he's going to add some water to them. So let's see what happens.
Over there. The drinking water dispenser is clearly marked.
Thank you very much, sir. Yusuf.
Help yourself, Commodore. Slake your thirst. sensation when we're through with you.
Perhaps. But I am appalled by your attitude.
Now notice there's something going on here. He's accidentally switched the drinking water to heavy water. That's something we'll come back to later. But he hasn't noticed.
Coming, Batman. I'm coming at once. Holy hallucination!
I wish it were, Robin, but it's not. It's 5 dehydrated pirates rehydrated.
So there we are. It's 5 dehydrated pirates rehydrated. Well, would that happen? Well, of course it wouldn't. Okay. Let's try this with the sugar. So this is our dehydrated sugar. Adding some water to this, well, we certainly don't get our sugar back. Okay. This is an example of an irreversible change. The copper sulfate, when we heated that up, it drove the water out, and when we add the water back, it reforms the hydrated copper sulfate. But this sugar here has been totally destroyed when the water has been removed, when we're left with the carbon, and we cannot reverse this reaction. And of course, it would be the same for us. If we removed all the water from us, you certainly couldn't regenerate a human again by adding the water back. Okay, so that's some reactions there where we've taken water out and added back in again. Okay, but so now we're going to look at water itself. So what exactly is water? Well, we're all familiar with water. It's a liquid and we drink it, and it has the formula H2O. What exactly does this mean, H2O? Well, it means that the water molecules are composed of 2 atoms of hydrogen and 1 atom of oxygen. And we can see these if we split up the water. Putting energy in can be used, we can split up the water into its components, oxygen gas and hydrogen gas. And this is what's going on here. So the electrical energy being passed through the water in these tubes here is splitting up the water, and we're seeing bubbles of gas forming. And these are pure hydrogen gas and oxygen gas. Now, which one's which? Well, looking at the tubes here, we see that there's more gas produced on this side than there is on this side. In fact, there's about twice as much gas on this side as on this side. This is the hydrogen gas, and this is the oxygen gas. So there's 2 parts hydrogen to 1 part oxygen, which is, of course, why the formula for water is H2O, and why the models that we have hanging around the lecture theatre, each molecule of water is made up of 1 atom of oxygen, coloured red, and 2 atoms of hydrogen, which are white. Okay, so that's a molecule of water. Now, we can show the equation for this reaction where we're splitting up the water. This, we have our water, or hydrogen oxide, as somebody might call it. So we're putting energy into this, and we're splitting it up, and we get the gases, hydrogen and oxygen, in the ratio 2:1. So now we're going to have a look at these gases and see the properties of these. So first of all, we'll start with the gas hydrogen. Okay, so here is a balloon full of hydrogen, and of course we notice one of the properties of this gas, and that is it's much lighter than air. In fact, hydrogen is the lightest substance in the universe. Okay. This means we could use it to fill our balloons, our party balloons, or even airships, and here is the Hindenburg filled up with hydrogen gas. Now, actually, we don't fill our balloons with hydrogen, and this is for a very good reason. Despite it being the lightest substance in the universe, it's also rather flammable. And this is what happened to the Hindenburg. Okay? It crashed and burnt. So, well, let's see if we can try this with our balloon here. So this is a balloon filled with hydrogen gas. Apply a light, and it goes up. Okay, right. Notice our sugar is beginning to react quite vigorously there. Okay, there's actually a lot of heat being formed from this reaction, and that's creating steam, which is causing some of the bubbles and the carbon there that's forming to rise up. But anyway, so that's the sugar's being dehydrated. Anyway, back to our gases. So we've seen then the reaction of hydrogen. This is hydrogen now recombining with the oxygen in the air, and this forms hydrogen oxide, or water. We don't see the water because actually it's instantly vaporized and spread out the room as water vapor. So we don't see that, but it's reforming the water, and it's also liberating a lot of energy. And no doubt you felt the energy there as the hydrogen and oxygen recombined. Well, here we have another balloon. This balloon is filled with pure oxygen gas. Now, of course, notice this time, this isn't floating up in the air. We've had to tie it to the retort stand here. And this is because oxygen is not lighter than air. It's about the same density. Not surprising, of course, because oxygen is one of the main components in the air. About 20% of the air is oxygen. Now, watch what happens when I apply a light to pure oxygen gas. Okay, are you ready? Not a lot. Okay, well, oxygen is not flammable. Oxygen doesn't burn. Oxygen allows things to burn, but itself doesn't burn. The hydrogen burnt very nicely because it was reacting with the oxygen that was in the air. The oxygen had nothing to do. Now, we've seen then that hydrogen can recombine with oxygen to form water. The question is, what ratio do we need to mix our hydrogen gas and our oxygen in to get the biggest bang, to get the best reaction? So this balloon here, the white balloon, is filled up with equal measures of hydrogen gas and oxygen gas. Okay? Now, see if this is any louder than the hydrogen itself. Now, the hydrogen balloon was bigger. It was a bigger balloon. But see if this one's louder. Let's listen. Okay, you ready? Yeah, I thought that was slightly louder. So that one was equal amounts of hydrogen and oxygen. Now this balloon contains twice as much oxygen. So this one has got 2 parts oxygen to 1 part hydrogen. Okay? Well, let's see if this one is any louder. Are we ready? No, not really. Wasn't quite the best mix. So what is the best ratio to mix these gases? We've had 1-to-1. That was pretty good, but I think we can do better. So what would the best ratio be? Any hands? Yep.
2 parts hydrogen, 1 part.
You're absolutely correct. 2 parts hydrogen to 1 part oxygen. And we know that this is right because the chemical formula for water is H2O. That means each molecule contains 2 atoms of hydrogen, 1 atom of oxygen. So that's the best ratio to mix them. Well, let's try this one then. This is 2 parts hydrogen, 1 part oxygen. And that was pretty loud. Okay, well, we can use the results of that experiment there to understand the next reaction. Mark's just filling up a tin can for me with hydrogen. So this tin can contains pure hydrogen gas, and it's got a little hole in the top. And I'm just about to light it. Okay, are we ready? There we are. And there's another one over here, and I'll light that one. Now, what's going on? The hydrogen is, of course, lighter than air, as we've seen. And the hydrogen gas is coming out the top of the tin cans, and we lit it, and it's quietly burning away with the oxygen in the air. Now, the same time the hydrogen is coming out, there's also a little hole in the bottom where the air is coming in. And we've seen what happens if you get the mixture of oxygen and hydrogen just right. Well, then more violent reaction takes place. I think that one wasn't quite filled properly. This one should go a little bit better. Okay, so say hydrogen coming out, burning quietly, air is coming in the bottom, and we're going to get just the right mix in any second. Okay, now, so we've seen the reaction of hydrogen and oxygen, and when we get it mixed just right, get a nice loud bang. And I need a volunteer for this next experiment. But I'm afraid it has to be a volunteer who has insurance. Okay, so that sort of narrows it down a bit. I'm not sure you've got insurance. I think Paul here.
Me?
Yes. Yes. Exactly. The university is insured, so I'm sure Paul will be okay. Right. Okay, so goggles on. Right, now then, I'd like you to hold out your hand. What I'm going to do is we're going to explode some hydrogen and oxygen in just the right ratio in Paul's hand. Okay?
Do I need goggles on?
Sorry? Well, maybe. Right, so I'm just going to put in some, this is washing up liquid at the moment. If you just contain that, that's it, that's good. So, that's it, keep it in there, that's good. It's shaking, don't know why. Now, over here, we're splitting up some water using an electrical current, just as we did before. And remember, we get the hydrogen and oxygen gas given out in just the right ratios, 2 to 1. And we're combining these gases together, we're mixing them up, and making lots of bubbles on the hand. Perhaps you can just hold that for a second while I stand over here. Okay? No, no, only kidding, no. We're going to put some earmuffs on you, Paul, okay? So you just keep doing that. Yep, okay, we'll have those on there. Okay, all right. Good, now we can say what we like. Okay, now, have you got enough yet? Not quite, need to get a few bit more here. If you just keep holding that, that's good. Okay, now I'm going to light it. Thank you, Paul. So, hand out. Okay, are we ready? Oh, well, very good, thank you. Great. Thank you, Paul. Right. Okay, so I hope you've still got all your fingers. Now then, so we've looked at the gases, hydrogen and oxygen, that make up water. We're now going to look at water itself. And water, well, it's a liquid, but what exactly is a liquid? Well, this is actually quite tricky. Before we look at a liquid, perhaps we should look at the solid. Solid is in many ways easier to understand. So here I have some solid water, also known as ice. Okay? Now, what does this look like? If we could look very, very closely and see all the molecules in this, we would see that they were all arranged in a regular pattern, okay, rather like this sort of thing. Okay? So we still have our water molecules intact with each oxygen connected to 2 hydrogens, so here they are, but now they're all linked together in a regular pattern. But as the thing warms up, so we give it some energy, it warms up, the molecules start moving about, and we get a liquid. And they're still sort of connected together in lumps like this, okay, but they tend to go all over the place, like that, okay? But they're sticking together and moving around. Well, this is sort of what a liquid is like. Right, now, we have an animation here to show what liquid water is like. This was actually made in the department here using a supercomputer to calculate what would 32 molecules of water, the same number that we have hanging from the ceiling here in the mobile, what they would look like at about 30 degrees C. Now notice they're all jiggling around. Also notice that during this, as they're moving around, we see some of the yellow dotted bonds forming and disappearing, reforming, disappearing. These are called hydrogen bonds, and these are weaker interactions than the interactions between the hydrogen atoms and the oxygen atoms themselves. But these hydrogen bonds form momentarily and then disappear, but it's these that actually hold the water molecules together and keep water as a liquid. So rather than being a gas, the water is a liquid because the 2 water molecules or more are held together by these weaker interactions called hydrogen bonds. So we can still separate them, and these hydrogen bonds form and reform and stick together like so. Okay, and it's these that keep the molecules together as liquid water. Now, why do we get these hydrogen bonding interactions? What are they? These are actually due to the charge in the water molecule being arranged in, well, not in a symmetrical fashion. More of the negative charge is associated with the oxygen, and more of the positive charge with the hydrogens here. And so this means, well, they can connect together, but they always connect together with one hydrogen connecting to the oxygen, hydrogen to oxygen from the separate water molecules. That's how they stick together. I can show this with a magnet with this stream of water here. If I bring a magnet to it, we see that we can deflect it, okay? But I can actually show this with real water as well. And for this, I need a volunteer. And there was a very keen, oh yes, you're very keen. Yes, if you can come down, please. Okay, what's your name then, please? Sorry, Julian? Julian, okay, if you can come over here then, please. All right, now, all I want you to do is I'm going to open this tap in a minute and let the water out. and you just want to catch the water in the bucket. If you come down here to make it a little bit harder for you, okay, so you're going to catch the water. You ready? It's very tricky. You ready? Okay. Oh, you missed it. That's it. Move. That's it. It's over there. Right, now you just catch that. Is that difficult or is it easy? Easy. Ha, right. So what I've got here is a plastic rod, and I can charge this up with some static electricity by rubbing it. Okay, so give it a good rub here. Now watch what happens when I bring it near to the stream of water. It's deflected. Let's try this again. Whoa. Catch it, move, catch it. Ah. Okay, bit harder now, isn't it? Yeah, okay, well, thank you very much. It's a little bit wet, thank you. So what was happening there, the static electricity in the charged rod could deflect the stream of water, but this could only happen because of the unsymmetrical distribution of the charge around each water molecule. More charge, more negative charge on the oxygens, more positive charge over the hydrogens. And it's these that give rise to the hydrogen bonding. Okay, well, we all know what temperature we need to cool the water down to make ice. So what temperature do we need to cool the water down to make ice? 0 degrees centigrade. Okay, good, yes. Now we have some ice here, ice and water, and it is indeed at 0 degrees. And at 0 degrees C exactly, we have water going to ice and ice going to water. We say that they're in equilibrium. Okay? Below 0 degrees, water should be ice. Well, it should be ice, but if we're very, very careful, we can actually make liquid water. We can keep the water liquid at temperatures less than 0 degrees. So I have some here. This is called supercooled water. So this water is actually at -6 degrees. So it's still liquid. We have to cool it very, very slowly and carefully. But watch what happens if I just add a tiny crystal of ice to the top. It instantly freezes. So here it's freezing now. And this is because the water should be ice at temperatures lower than 0. Okay, and now it is ice. There's a little bit of water left, but it's ice. Okay, but if we're very careful and use a very clean tube, if we can have another one then, please, thank you. So using a very clean tube and very pure water and cooling it down very, very slowly, well, it can still stay as water. So it's water now, and I can just start this just with a little help, giving it something for the crystals to form on. Even a speck of dust would do this. But now we can see that the water, the supercooled water, is turning into ice, as it should be at 0 degrees. Okay, at temperatures less than 0. Okay, and now, again, it's frozen solid. Okay, so that's supercooled water at temperatures less than 0. Now, ice is also a very interesting substance in its own right. Solid water. There's a very unusual property of solid water, and that is that it floats on top of liquid water. Well, you might think nothing very exciting about that. We all know that ice floats on top of water. After all, icebergs float. But actually, it is very unusual. Here we have some solid cyclohexanol. We've just added this to the liquid cyclohexanol, and this one actually sinks. In fact, this is the usual case. It's more normal for a solid substance to sink when we put it in its liquid. It's actually very unusual that water floats when it's ice on top of liquid water. But nonetheless, it's a good thing that it does, because this means that when temperatures drop, and if we've got to have a pond filled with water, the surface freezes, but rather than that ice dropping down to the bottom and then more ice forming and then that dropping down to the bottom and the entire pond freezing, it means that only the top freezes and the ice floats on top, which means underneath it's insulated from the cold air by the layer of ice above, and so the fishes can still survive, which is great. Okay, it'd be bad for fishes if ice sank. Okay, now, we'll come back to exactly why ice floats, but we've got one more demonstration to show you involving this, and I need to come over here. And I have a metal container here made of cast iron, and I'm going to fill this now with water. So we'll fill this up. So this is now filled with liquid water right to the brim. This is made of, let's say, cast iron, so it's pretty strong. And I'm just going to do this up completely, so it's really tight. So at the moment then we've got the container filled with liquid water, but in a minute I'm going to freeze this to turn the liquid water into solid water, into ice. Now we're going to lower the metal container here into this bath in here that contains a very, very cold liquid, so this is going to freeze the water. But as you've seen, as we freeze the water, well, the ice takes up more space than the liquid form. So I'm going to lower it into the container here. Oops, hopefully. Maybe. Yes. There we are, made it. So this is now in the very cold liquid, and the water is turning into ice. So, let's have a look at our ice crystals again. So here we have a crystal of ice. In the ordered array that we see here, well, there seems to be lots of space. So as the liquid arranges itself, the liquid water arranges itself, and we get this ordered crystal structure in ice, there's actually quite a lot of space in it. As the ice melts, it takes up less space. And this means if we had the solid ice, it would actually float on top because it takes up more space. Now, this is what's going on here. We've taken the liquid water and we're cooling it down to make the solid ice, but the ice takes up more space than the liquid. But there's nowhere for this to expand because the metal container was absolutely filled to the brim with water. So this means that the pressure is building up inside here, and now it's exploded. Okay. So this is one from an earlier lecture, and you can see that actually this was pretty thick cast iron. Oops, that's the top fell off. Pretty thick cast iron, okay? And it's just the pressure as the water changes to ice that's broken that. And of course, this is very important. I don't know if any of you had your water pipes burst. Water pipes can burst because, again, as the water cools, turns to ice, the ice expands, takes up more space than the liquid, and that can actually burst the pipe. So when the water thaws again, it all comes out. Right, well, if we give water even more energy, we can change it not from ice to water, but all the way to steam. Okay, so we're now given this lots of energy, and what's happened now? Well, we still have our individual water molecules. They're still intact. We have one oxygen and two hydrogens still together, but now all of the molecules are separated by lots of space. So some of them come all the way over here. Okay, so there's lots of space between them now. This means that if we heat up the water to make steam, it takes up much more space, much more space. Well, perhaps you might like to guess how much more space water takes up if you turn it into steam. So let's have a guess. Let's have somebody at the front here. How much more space do you think it takes up? No, anyone? Yes, how much?
20 gallons.
20 gallons. Oh, that's an unusual measurement, but OK. Well, we've got an instrument over here to measure this. We're going to see how much 1 milliliter turns into. OK, so on our dial here, we need to watch very carefully. We're going to see 1 milliliter, and it turns into how many milliliters? Well, let's have another guess. Yes, what do you think? How many? Someone down here saying 100, perhaps. 100 milliliters, what could be. Well, let's try the experiment. Are you ready there, Chris? OK, so just put this in. So now this is a giant syringe here, made of glass, and we're heating this up to very high temperatures. OK. And in a second, we're going to inject into this just 1 milliliter of liquid water. Keep going. OK, that's good. Now, you need to watch the dial very carefully. OK, I'm going to inject 1 milliliter of liquid water into the apparatus, and you keep an eye on the dial. because we need to see how many millilitres of steam we get from this. Okay, 1 millilitre about to go in now. Okay, how many have we got? 100, 300, right? 4, 500, 600, still going, still boiling, 700, 800, still going, 900. Is it going to get to 1,000? Yes, that's 1,000. So this is, remember, 1 millilitre of water. It's turned into 1,100, and it's still expanding. Okay, remember this is because there's now lots of space between these. That's 1,200, still expanding, still increasing. Okay, I'm going to come behind here now. We're up to 1,300, and still going. Okay, so the point is then that 1 millilitre turns into, well, it's going to be well over 1,500 millilitres of steam. And this is because now there's a lot of space in between these. The molecules are moving around very, very quickly. Lots of space in between them when they're a gas. Okay, well, we'll leave that one going for a little bit longer. But while we do that, I'm going to set up another experiment over here. And over here, we have 1 millilitre of water again, but this time it's in a sealed tube. And I'm going to do something rather silly, and that's heat up this with a Bunsen flame. So we'll keep a camera on this now. So we've got 1 millilitre of water being heated up, but this time it's in a sealed tube, so there's nowhere for the water to escape, and there's nowhere for the steam to escape either. And we've seen that 1 millilitre turns into, well, I think we've lost count now, but it's almost 2,000 millilitres of steam. So we'll just turn this off. Now, what's going to happen over here? We have our water being heated up, turning into steam, but there's nowhere for the steam to go. This means the pressure inside this glass vessel is building up, building up, building up, nowhere for it to escape. Now, what's going to happen? Something's got to give. And what's going to give is the glass container. So watch very carefully. You can see the glass tube there now, and it's heating up. The water is turning into steam, which should take up much more space, but it's now gone. And there's nothing left of this glass container whatsoever. All there is at the bottom here are tiny, tiny little fragments of glass. It looks like sand. This is some from the earlier lectures. So it's just powdered glass now. And that's because the liquid water, when we convert it to the gas takes up so much more space. Okay. Right, so we've seen that we can convert ice to water by heating it up, and if we heat it up still further, we get steam. Now, we all know what temperature water boils at. Okay, so what temperature does water boil at? Want to shout it out? 100, yes, very good. So now, being true scientists, we should check this. We should do an experiment. So I shall take some water in my paper cup here, fill it up with water, and we're going to test to make sure that water boils at 100 degrees C. So I'm going to bring it round here, and we're going to heat it up. We'll check the temperature. There we are. So the temperature now is at 20 degrees. I'm going to heat it up with a Bunsen. Okay. Now, is this a sensible thing to do? A good experiment? Is this a good, well-designed experiment? Well, let's see. Okay. Now, interestingly, the paper cup is not burning. And this is because all of the energy from my Bunsen flame here is actually going into heating up the water. Now, the paper can't burn until it gets to a hot enough temperature, but the water is taking all the energy. So rather than heating the paper up at the moment, all the energy is going into heating up the water. So the water is now at 37 degrees C, 39. It's heating up. Well, we'll see what temperature this boils at. Actually, I think Chris can give me a hand with this, please. So, Chris, where is Chris? Here he comes. Perhaps you can just give me a hand heating up the water, please. Okay? Keep that there. Don't burn it. Thank you. Now, I have some water over here that we're actually heating up. This water, as you can see on the scale here, is boiling, and it's boiling at 100 degrees C. This water over here is only at, well, it's 85 at the moment. But we're going to see if we can make this boil at a temperature less than 100 degrees. While we're at it, I'm going to get my dinner on the go. So I'm going to have eggs, boiled eggs, I think. I need somebody to time this. Can I have someone, would you be able to time this for me, please? If you just start the stopwatch there when I say, just press the button. Okay, we're going to start the stopwatch when I put my eggs in. So we'll have 1 egg in the water here. We'll start this one first. This is in the water at 85. I'll just put the lid on. And we'll put 1 in the water here at 100. This water is already boiling. Okay, and actually the temperature here is it's dropped now to 77, 76 degrees C, and it's dropping, but the water is actually boiling. This water is boiling at 100. This water is boiling at, well, it's at 73 degrees C now, but it really is boiling. Now, why on earth is this water boiling at only 70 degrees, whereas normally we know that water boils at 100? Before I answer this one, I need to put the rest of my dinner on. I'm going to have egg and chips. So I need to heat up some oil. I need to get that on the go. Here's some oil. Mark, have you done me some chips? Where are the chips? There. Oh, there? Mark's done me 1 chip. Okay. I think he's trying to tell me something here. Okay, well, since he's only done 1, I'm going to use a very small beaker. So we've got one down here already. I'm just going to put some oil in and get this heating. Oops. Okay, so just put the Bunsen on. There we are. Get that ready. Okay, better put a screen around it just to be safe. Okay, wouldn't want any accidents. Okay, perfect. Thank you. So that's the oil heating up. We'll come back to that later. Now then, back to this water. So water normally boils at 100. This water is boiling at 100, but this water is boiling at, well, it's at 71 degrees C. This is because, well, what we've done here, we put a lid on this, and we've taken some of the air away from this space here. So we've reduced the air pressure. And actually, we've reduced the air pressure to the same as it would be on the top of Mount Everest. Now, if you climbed up Mount Everest, you may know that you'd need to have oxygen gas if you wanted to do it safely, okay, as safely as you can do it. And this is because the air on the top of Mount Everest is very thin. There's less atmosphere there. It's actually about 1/3 of the pressure as it is here in the lecture theatre. Now, why does this affect the boiling point? Well, I have some specially trained volunteers. They know who they are. If they can come down and get prepared, please. So we're trying to explain then why water normally boils at 100 degrees C at normal atmospheric pressure, but only 70 degrees on the top of Mount Everest. Right. Now then, so I need some water molecules, and they're over there, and some air molecules. These balls here represent air molecules, okay? And can I have my water molecules, please? Water, come this way. Okay, here come the specially trained water molecules, and you see they've got lots of energy, and they're bouncing around, as we've seen water does, and they've got quite a bit of energy, and they would like to get apart from each other, but the air is bashing them back. Okay, so the air bashes them back, and this means only when they've got enough energy to overcome the air molecules bashing into them can they boil and turn into gas. And that normally happens at atmospheric pressure at 100 degrees. But if there's less air around, and that's like we have on the top of Mount Everest, then they can boil, and they come out and they're boiling now, as you can see. They can escape, And this is because there's only a limited amount of air bashing them back. Okay, they can boil very easily. So as you see, they keep coming this way, don't they? Boiling until the little bit of air. So that's it, you see. The lower pressure means they can't fully boil. Thank you very much, water molecules. So, at the reduced air pressure on top of Mount Everest, water would only boil at 70 degrees C. This means you can't make a decent cup of tea on the top of Mount Everest, but also, well, can you cook an egg? That's the question, and this is what we're going to try and find out now. Okay? Can you boil an egg on the top of Mount Everest? Now, how are we doing for time? How long have we had so far? What's that? About 4 minutes, okay. We'll probably need a little bit longer for my hard-boiled egg to cook, so we'll leave that just a little bit longer. We'll look at one of the other properties of water now, and that's that, well, of course, things dissolve in water. I have some crystals here of potassium permanganate, and I'm using these because they're very brightly coloured, but adding these to water, they dissolve very easily, and we get this intense purple colour. Okay, so some things dissolve very easily in water. Another thing that dissolves is, well, this crystal that I have down here. Right. This is a crystal, well, it represents a crystal of sodium chloride. And we have the green chloride ions here, the silver sodium ions here, and they're held together in this regular lattice, in this solid structure here. This is sodium chloride. This sodium chloride is also known as salt. Very good. Salt dissolves in water. And here I have a small crystal of salt. How does salt dissolve in water? Well, the water molecules can stick to the ions that we have in the solid. So, for instance, all the waters here can stick to the sodium ions, and these help pull apart the ions. And what we eventually have are separated ions, but they are surrounded by the waters. So we end up with the waters separating the ions and sticking to the ions and pulling them apart. Okay? So that's how something like sodium chloride dissolves. Other things, though, don't dissolve in water. For instance, sand. That doesn't dissolve in water, which is just as well, because if they did, of course, every time the ocean came in, the sea came in, all the beaches would wash away. Another thing that doesn't dissolve is oil. Okay? So oil and water. I have some coloured water here. We've added a bit of blue colouring. Mixing this with the oil, or the oil just sits on top. Okay? It doesn't mix with the water. It floats on top. And this is because, well, the water would rather stick to itself than stick to the oil. Okay? So the water is sticking to itself, and this is because of all the hydrogen bonds in the water. That's keeping the water stuck to itself rather than mixing with the oil. So some things mix, some things don't mix. Okay, I think it must be time to test our eggs now to see if we can boil an egg on the top of Mount Everest. How are we doing for time? What's the time, please? 7.5 minutes. Okay, well, we'll see if that's long enough to cook an egg then, shall we? Now, I need a special volunteer for this one, and it's got to be a special one because you won't want to volunteer for this. You really won't. I need, Chris. Chris, would you like to come here? All right, Chris, have a seat here, okay?
I burnt the cup again, didn't I?
You burnt the cup, exactly, and now you're going to test the eggs. So first of all, I have the egg that we boiled at normal pressure, at atmospheric pressure, okay? Boiling at 100 degrees C. I think we should test it on Chris's head. What do you think? Yes? Yes. I think not quite that cruel. We'll give him a hat, okay? Health and safety, okay? Nicely cooked. Right, can we cook an egg on the top of Everest? What do you think, Chris? Can we do it? Okay, well, let's see. No. Oh, sorry, Chris. There we are. Thank you. Thank you very much. Hold on. I've just noticed we have a fire over here. we have a fire. The oil has caught fire. I need to get my fireman's outfit on here. Okay, it's actually caught fire. So much for my chips. Okay, let me just put this on and my hat here. Okay, put this on. Oh, where's the hole? Yeah, there we are, right. Oops, okay, right, put this on. And the jacket. Now, I'm going to put the fire out, but actually, I'm going to do something really silly. Really silly, and this is adding water to burning oil. And this is something that you should never do. Okay, so I have some water here, and we have some burning oil over here. Now, what happens? Well, the oil is at very high temperatures. As soon as it comes into contact with the water, it's going to turn into steam. And we know that the steam takes up about 2,000 times the volume of the liquid. We also know that the water sinks to the bottom of the oil, and it's going to instantly turn into steam, and watch what happens. Okay, right, I'm just going to add, we've got a tiny little bit of oil, add some water. Whew. Okay, right, going to heavy water. So you remember from the Batman film, this was where the penguin accidentally knocked the switch over. So instead of having drinking water, he ended up with heavy water. Now, what on earth is heavy water? Well, I have here 3 identical flasks. One of these is just an empty flask, and I'm going to set the balance to 0 for this. And in this flask, identical flask with 100 milliliters of water, okay, so we've taken into account the weight of the flask, but we see that 100 milliliters of water weighs, well, it's just about 100 grams. Okay, that's the density of water is 1 gram per centimeter cubed or per milliliter. Now here I have some heavy water, and it's exactly the same amount. It's 100 mils, 100 milliliters of water, and this weighs 110 grams. Okay, so this is heavy water. Now, what exactly is heavy water? Well, in order to understand this, we need to look right into the heart of a hydrogen atom. So remember that water is made up of 1 oxygen and 2 hydrogen atoms, but we need to look inside this to see what a hydrogen atom actually looks like. What is it like? Well, if we looked inside, we would see the atom itself, the hydrogen atom. This is a normal hydrogen atom. There's an electron that whizzes round. Okay, this is whizzing around all over the place. This is negatively charged. And then in the center of the atom, in the nucleus, where all the weight of the hydrogen atom is, there's a proton. Okay, and that's what gives the hydrogen atom its weight. Well, a heavy hydrogen atom is a different type of hydrogen. It still has the same chemical properties pretty much as normal hydrogen, but this one still has 1 electron, still has 1 proton, and that's the thing that makes it a hydrogen atom. But this time it has a neutron as well, and the neutron has about the same mass as the proton, and this means that the mass of the hydrogen atom now, the heavy hydrogen, is actually twice that of a normal one. Well, remember, the water here is made up of 2 hydrogens and 1 oxygen. The oxygen hasn't changed, and so just replacing the normal hydrogens with these heavy hydrogens, sometimes called deuterium atoms, it means that the heavy water now, rather than weighing 100 grams, weighs 110. And this is actually rather interesting. I promised that I'd tell you why water is blue, and this is another really unusual thing about water. Now, most things absorb energy, and they absorb energy to make the molecules vibrate. Okay? So it's all to do with vibrations. Right, so imagine I'm a water molecule. I'm going to be vibrating. Okay? And I can vibrate in all sorts of different ways like this. This is how water molecules vibrate. And this actually, for most compounds, when they're vibrating away, they absorb energy in the infrared part of the spectrum. Okay? So most things absorb in the infrared. Oh, that's enough of that. So here's infrared. This is infrared light. Everything when it's vibrating. So actually, maybe when you hurt yourself and you go to the doctors, they sometimes put an infrared lamp on, and it feels warm. It feels warm because it's making your molecules vibrate. Most things absorb in the infrared. Okay, so here is infrared, it's about here. And this is increase in energy. We've got all sorts of energy here, from radio waves, microwaves, infrared, visible, X-rays, really bad, gamma rays, bad. Okay, but most things absorb when they're vibrating in the infrared. Okay, now, so we need to look at vibrating molecules. I have over here a vibrating molecule. This is, well, just one hydrogen atom. Okay, and let's start this one vibrating. Here it is, vibrating nicely. And I have another hydrogen atom over here. And so remember, I have two hydrogen atoms in a water molecule. So here's another one. And I'm going to start this one vibrating. And if I can get it timed right, you see that it vibrates at the same speed. Okay, fine. Well, when I add the extra neutron to this one, watch what happens to its vibration speed. So let's stop this one and add the neutron on. So this is now making heavy hydrogen, or deuterium. And watch the bouncing rate now. Much slower. Okay? And this is the point. So most things vibrate relatively slowly, like the heavy water does here. Okay? But normal hydrogen and normal water vibrates pretty quickly. And it vibrates so quickly that it actually doesn't absorb infrared. Well, it does absorb infrared, but it also absorbs higher energy light, creeps out of the infrared, and just absorbs red light. Anything that absorbs red light looks blue. Okay, so here is a blue filter. If I look through this, I can't see any red. No red light is coming through. It's been absorbed by this, and that's why everything looks blue. I can show this with my red laser here. Shining the red laser on this, the red light is stopped. It doesn't go through this. This color here, this filter, absorbs red and it looks blue. And that's what happens with normal water. Because it's vibrating so quickly, it actually absorbs in the red part of the spectrum rather than, as everything else does, in the infrared part. And this is why water looks blue. Actually, we have this set up down the bottom here, and you can come and have a look later. We have two tubes. One of them is filled with heavy water, and if you look through here, you will see that this actually looks white in the white light that we have at the other end, whereas the water, if you look through there, it really is blue. So water is blue not because of the sky reflecting on it when we look at a picture of the Earth, but actually because of the inherent vibrations of the water molecule. This is just another special thing about water. That's just about the end of the lecture. One thing I should say is I forgot to mention in all the haste here how you should put out an oil fire. So if ever you do have some burning oil, like we had here, you should never add water to this, because as we've seen, the water is instantly turned into steam and it sprays the burning oil everywhere. In fact, many homes have burnt down because of people trying to put out oil fires with water. Of course, what you should do is take a cloth, put it under the tap, wring it out, so you've got a damp cloth, and then just put this over the oil, and then that will suffocate it. It will stop the air getting to it, and it will put the fire out. I think we should finish with a bit of a bang. I hope you've had a good day, and I hope you've enjoyed the lecture. This is the reaction of hydrogen with the oxygen from the air forming water. Thank you very much indeed. Thank you.